Hello everyone, thanks for watching this video. My name is Hui Guo. I'm going to introduce our work, DEUA, which is short for Diffusion Epistemic Uncertainty with Asymmetric Learning for Diffusion-Generated Image Detection. This is the outline of today's talk. Firstly, I will introduce the background of diffusion-generated images detection and uncertainty estimation. With the development of diffusion models, there is a growing need for effective methods to detect these highly realistic generated images. Recent detection features, including obvious artifacts and statistical features, among which reconstruction error-based methods showed potential. But these methods struggle to generalize to data with unfamiliar patterns. Here's a brief introduction to a diffusion model. A diffusion model typically involves two processes. The for process defines the distribution at step t, given step t plus 1, while the reverse process defines the opposite. In diffusion process, uncertainty, both epistemic and aleatoric, significantly impacts statistical features for fake image detection. It is essential to disentangle the overall uncertainty and focus on effective features for this fake image detection. Here's a brief introduction to epistemic uncertainty. Epistemic uncertainty can be modeled by placing a prior distribution P of theta over the model's parameters. M P of theta given dataset D can be computed with the Laplacian approximation, where sigma is estimated by Hessian approximation or the last layer Laplacian approximation. Secondly, we analyze why uncertainty matters in diffusion-generated image detection. We find that relying on diffusion-based measurements to identify generated image can become misleading when aleatoric uncertainty dominates. This figure shows diffusion reconstruction error in different steps due to aleatoric uncertainty. We can see that the difference in reconstruction error becomes less significant compared to the standard deviation caused by aleatoric uncertainty. Both aleatoric and epistemic uncertainty contribute to diffusion reconstruction error. Relying solely on reconstruction error is less effective for real and fake image distinction when aleatoric uncertainty is high, but epistemic uncertainty rises significantly for out-of-chain domain samples, providing a more reliable basis for anomaly detection. In this figure, aleatoric uncertainty causes overlapping between real and fake images, which is nearly the same in reconstruction error distributions when aleatoric uncertainty is high, and only epistemic uncertainty accurately distinguishes these two types of samples. To address the issues discussed above, we present our proposed method, DEUA, which includes diffusion epistemic uncertainty, feature estimation, and asymmetric learning method. To estimate epistemic uncertainty of diffusion models, we further construct a Bayesian diffusion model by placing a prior distribution P of theta. We use last layer Laplacian approximation to approximate P of theta given dataset D. Then, via the Monte Carlo approximation, we calculate the epistemic uncertainty using the following equations. Check this figure of our workflow. Let U be the spatially aligned epistemic uncertainty, and V be the visual feature map. The global epistemic uncertainty feature Z of U is computed by applying attention pooling on U. The refined visual feature is computed with a multi-head attention module. And finally, we have feature Z for fake image detection. To learn an even decision boundary with larger margins while preserving the information content of the representation, asymmetric learning is proposed. Then the overall loss function is constructed as a weighted average of cross-entropy loss and the asymmetric consciousness loss. Next, we will present the experimental setting and results. We conduct extensive evaluations on two large-scale datasets, Gen-Image and DRCT2M. Additionally, we performed generalizability comparison and cross-data experiments. In the Gen-Image benchmark, our method outperformed the state-of-the-art by 6.5% without DRCT-DR and by 2.4% with DRCT-DR. For generalization across generators, Gen-Image experiments showed our method suffers less performance degradation across subsets from diverse generators, achieving an overall average accuracy of 85.6%, where DRCT2M experiments also confirms these comparable potentials. Through experiments involving more generators, DEUA achieved competitive or superior performance compared to existing unified detectors, both on the universal fake detect datasets and on novel generator paradigms including diffusion transformers and autoregressive models. Experiments on cross-data set generalizability showed that diffusion reconstruction error-based methods, such as DEUA or Layer 2, faced substantial performance degradation across data sets, while DEUA remained competitive and effective in large frameworks. Here, we investigate the individual components of our method and their respective impacts. As observed, each component delivers independent performance improvements. Furthermore, we find that the contribution of DEUA dominates overall performance. This validates the effectiveness of the feature. Finally, let's draw the conclusion. In this work, we propose a novel framework for detecting diffusion-generated images with a DEUA. Experiment results demonstrate that our framework, particularly the diffusion epistemic uncertainty component, achieved state-of-the-art generalizability across a variety of generation methods and datasets. Okay, that's all for this talk. Thank you for your time.